Hello. In this video, I would like to show you the basic rules of manipulating probabilities and some distributions for discrete data. Probabilities in many ways are at the heart of statistical analysis. So what are probabilities? Probabilities are a numerical quantity that expresses the likelihood of an event occurring. The probability, we often write as p, is between 0 and 1. So you cannot have probabilities that are negative, and you cannot have probabilities that are larger than 1. 0 denotes the event that never occurs, and 1 denotes the event that always occurs with certainty. You can think of probabilities in two ways. So-called frequentists believe that the probability of an event is the objective long-run frequency of the event occurring. So the probability of the event E would be the number of times E occurred across many chance operations. On the other hand, there's a school of probability theorists that think probabilities express more a subjective degree of beliefs. So the probability of an event occurring, given some background knowledge, is the probability of that these observations passt gut, da können wir noch mal. Genau. So how do you think of probability? Frequentists think of probability as the probability of an event being the objective long-run frequency with which this event occurs across many chance operations. On the other hand, there's a school of thought in probability theory called Bayesianism that believes that probabilities express subjective degrees of beliefs. For example, the probability of an event given some observations is the probability of these observations given that the event has occurred times our prior assumptions about how likely it is to observe that event. For most of the practical things we will do in this course, we follow a frequentist interpretation of probability. So, what are examples of probabilities? One of the most often mentioned examples, of course, is the coin toss, or the toss of a fair coin. In a fair coin, the probability that you observe heads or tails is equal to 0.5. If a coin is not fair but rigged, then this probability can also deviate. Another example of probabilities is the roll of a die. So in a typical die with 6 sides, the probability, for example, of observing an outcome of 3 is 1/6. There are rules with which probabilities can be combined and manipulated. The first one is, if you know the probability of 2 events, and these events are independent, so they don't influence each other, then the probability that both will occur is simply the product of the probabilities of them occurring individually. The second rule is how we find the probability of 2 mutually exclusive events occurring, or any of these occurring at the same time. So the probability of A or B is simply the probability of A plus the probability of B. What is the probability of one event given another event occurred? We can also compute that. And the probability of event A occurring given that event B occurred is the probability of event A occurring and event B occurring divided by the probability of event B. You can immediately see if these two events are completely independent, then we can use this rule here and plug in the product of the two individual probabilities into this and simply obtain the probability of A after removing probability of B from the denominator and the numerator. This of course makes sense, because if the two events are independent, then the presence of event B does not influence the probability of event A occurring. If there are dependencies between the two, they will show up in this computation. We can also compute the probability of an event not occurring, given that we know what the probability is that it occurs. And it's simply y minus the probability of the event. These are some basic rules of probability that we can frequently use to make our lives easier when we discuss other statistical topics. For example, in probability trees, these rules help us reason about the probability of events. Such probability trees you can often use, for example, in medical statistics to calculate the different outcomes of a study. Here, we very simply just have two consecutive coin tosses. So the first coin toss has possible results, heads and tails, each one occurring with a probability of 0.5. The second coin toss can either follow a coin toss that resulted in heads and then again be heads or tails, each again with a probability of 0.5. Of course, after tails has been tossed in the first toss, this is again possible for the second toss as well. So these two events, despite being done consecutively, don't influence each other. So if we want to compute the probability that heads occurred in the first toss and heads occurred in the second toss, these are the probabilities of two independent events, and we can simply multiply them together. So the probability that the event that we observe as the outcome of the entire experiment is heads and heads is simply the product of the individual probabilities, so 0.5 times 0.5, and that is 0.25. So this is the first of our probability rules in action. Of course, we can also use that to compute more complicated scenarios. So in this case here, this is about observing animals of a certain species with a certain color. And now the probabilities are not exactly the same. So with 0.3 probability, the animal will be black, and with 0.7 probability, the animal will be gray, the first animal that we observe. When we observe another animal, again, the chances to observe these colors have the same probabilities. So with our first probability rule for the event that we observe two black animals, we obtain a probability of 0.09 or 9%. On the other hand, to observe two gray animals, we find a probability of 0.49%. So say we now want to compute the probability that we observe two animals with the same color. So that would be the probability that either event A or event B occurs. So any of these two mutually exclusive events. Therefore, in this case, we can simply sum the probabilities of these two events and obtain a value of 0.58. Once we have calculated that, we can also very easily calculate the probability that we observe animals which don't have the same color, because by our last probability rule, this is simply 1 minus the probability that these animals have the same color. So in this case, 0.42. So what are random variables? It's a term that you often hear when you deal with statistics. A random variable is simply a function that maps the outcome of a chance distribution to a numerical value. That sounds terribly abstract. So let's say for a coin toss, our space of possible outcomes is simply heads or tails. To be able to compute with these events, we convert them to numbers, and this is what a random variable does. So the random variable x takes a value of 1 if the outcome of our chance operation, tossing a coin, is heads, and it takes a value of 0 if the outcome of our chance operation is tails. We then further have a probability function that assigns a probability to any of these outcomes. In the case of a coin toss of a fair coin, this will be 0.5 in both cases. Now we can actually look at probability distributions for certain kinds of data. In this video, we will only cover 2 distributions that apply to discrete data. In the next video, we will talk also about a probability distribution for continuous data. In this case, we have a binary random variable, for example, like in a coin toss, where the possible values that this random variable can take are either 1 or 0. The distribution is called Bernoulli distribution after a famous mathematician. The distribution has one parameter called p, and this is simply the probability that the random variable takes on a value of 1. Our function, the probability function, is this. It's p to the x times 1 minus p to the 1 minus x. If you think about what happens in this fairly complicated looking function, it's actually very simple. So if your random variable takes a value of 1, then this part of the equation will be p to the 1, so p. And this part of the equation will be, because 1 minus 1 is 0, will be just 1. So in this case, there will be just a probability of p for the event that the random variable takes on a value of 1. On the other hand, if the random variable takes on a value of 0, the former part will be 1, and you will have a probability of 1 minus p from the latter part for the event 0 occurring. We can compute with some math the mean and the standard deviation of a random variable that has a Bernoulli distribution, and we find that the mean is simply p, which also intuitively makes sense if p is the probability of observing a value of 1. The standard deviation is the square root of p times 1 minus p. We can graphically show a Bernoulli distribution like this. So on the x-axis, there are the different outcomes, 0 and 1. And here is a graph of probability between 0 and 1. The height of the graph shows the parameter p and 1 minus p. A second distribution for discrete data is the so-called binomial distribution. The binomial distribution you obtain by summing over individual trials with a Bernoulli distribution. The binomial distribution has 2 parts. On the one hand, there's this latter part, and this simply comes from the fact that we conduct independent Bernoulli trials that we sum. The former part here comes from the fact that the outcome of these Bernoulli trials is not in a fixed order, but all orders are possible. So here's a table showing for an n of 5, so n independent Bernoulli trials, the possible outcomes. So either we observe 0 successes and 5 failures. That would mean, for example, in the case of coin tosses, it would mean that we observe 5 times tails and 0 times heads. The probability for this event occurring would be p to the power of 0 and 1 minus p to the power of 5. Because in each individual repetition, the probability distribution follows a Bernoulli distribution, which is p to the power of x and 1 minus p to the power of 1 minus x. Of course, because these are 5 identical outcomes, it doesn't matter in which order you arrange them. It's always the same. So there's just one order in which they can be arranged. The same is true for the reverse event, that you always observe heads or always observe a success. Now, if we observe just 1 success and 4 failures, these can be arranged in many different ways. The latter part of the probability calculation in this case is clear. P to the 1 and 1 minus p to the power of 4. So how do we get this 5? We get it by computing the binomial coefficient for n equals 5 and j equals 1. Because this is still a fairly simple problem, we can also think about how this could be 5. It can be 5 because the success can occur at any of the 5 possible experiments that we did. The same is true if this is reversed. So for 4 successes and 1 failure, there's also 5 possible ways in which this can happen. Now the interesting bit are these two middle outcomes. So either 2 successes and 3 failures or 3 successes and 2 failures. In this case, it already starts getting a bit cumbersome to write down all the possible ways in which this event can occur. So by using this binomial coefficient, we can simply compute that number, and it is 10. That means there are 10 possible ways in which the outcomes can be arranged such that you have 2 successes and 3 failures. Let's have an example. So from a population of Drosophila, we draw 5 flies, and with a probability of 0.32, each of these flies is a mutant fly. So what are our probabilities that we observe 0, 1, 2, 3, 4, or 5 mutants in our entire sample? To obtain these numbers, we simply use this formula where n is 5 and p is 0.37. When we plug into this formula and we obtain the probability for observing 0 mutants, we find a probability of 0.1, and we indicate this by a small bar here. Then for 1 mutant, we find a probability of 0.29, and we indicate it by a slightly larger bar. Note that we didn't draw any white bars or anything like this here to stress the fact that this is really a discrete probability distribution that only has probability mass exactly at these numbers. So this is the binomial distribution. It has a mean of n times p, which is also fairly intuitive since you already know that the Bernoulli distribution has a mean of p, and we conduct n Bernoulli experiments. It has a standard deviation of square root n times p times 1 minus p. As I already mentioned, you can always think of the example of a fair coin, where p equals 0.5 and n equals 10, for example. That means for this binomial distribution, you would toss a coin 10 times and count how many times heads faces up. The mean across doing this experiment many times, this entire experiment many times, would be n times p, so 5. So on average, you would expect 5 heads to show up in your 10 repeated coin tosses. The standard deviation would be 10 times 0.5 times 1 minus 0.5, so square root of 2.5, which is 1.58. So how can we fit a binomial distribution to data? It's actually relatively simple, because it has only 2 parameters: the number of trials that were conducted and the probability in which every single trial results in a success or failure, or a 1 or a 0. So this is an interesting data set from the 19th century in England, where the number of boys and girls were looked at in very large families with at least 12, or with exactly 12 children. So in the data set, they observed the different outcomes with these frequencies. So in total, we have 6,115 children, and they were distributed across all these families like this. So how can we fit such a binomial distribution to data? We look at a data set from the 19th century in England, where a large number of families with exactly 12 children were analyzed. for these 12 children, it was always looked at how many boys and how many girls are represented among them. So in total, the dataset contained 6,115 families, and they were distributed like this. So very few had exactly 12 girls and 0 boys, and most often these values in the middle occurred. So how do we turn this into a binomial distribution? Well, if we say the probability of obtaining a boy and a girl is exactly the same, 0.5, then we can calculate the expected frequencies in this data set. The n in the binomial distribution is equal to 6,115. If we do that, we obtain the following values. What is interesting is if we now look at whether these expected frequencies are larger or smaller than the ones that we had observed in the data. We find that at the tails, at the extreme values, the data has always more mass or more families than expected, and in the middle, the data has less mass or fewer families than expected, which means that it's a bit more likely to have these extreme outcomes, so 12, 11, or 10 boys, or 12, 11, or 10 girls, than expected from a purely binomial distribution. Possibly hinting towards the fact that the children you get are not entirely independent from each other. So here you can see a fictitious example where this becomes very clear. So if we had observed 2,940 families with 12 girls and 0 boys, and 3,175 families with 12 boys and 0 girls, then we can likewise have the same expected frequencies because the ratio of boys to girls doesn't change. The ratio of boys to girls is what determines our parameter p for the binomial distribution. In this case, there would be many more observed families with 12 girls and 0 boys than we would expect from a binomial distribution, and many more observed families with 12 boys than expected from a binomial distribution. And we could clearly see that in this pattern of signs and how they differ from what is expected. So today we talked briefly about rules of manipulating probabilities and about the Bernoulli and the binomial distribution. These will repeatedly occur throughout the lecture when we analyze discrete data, and in particular data that are binary in nature. With that, thank you, and see you in the next video.